Okay, I know you've just been chomping at the bit to turn on this next video so you can understand why these units are what they are. Because this is supposed to be potential. It's supposed to be in volts. What's this Newton meter per Coulomb? Well, I'm going to do a little bit of a diversion here for a minute or so and tell you that 1 volt, by definition, a volt is something we've been talking about all semester. And it basically tells you, it's kind of like if you have a little charge that's at a certain potential here and you want to get to another potential or another height, it's kind of like a way to think about it being height for charges. And the unit for a volt is, it takes energy to get a charge from here to here. So if this is let's say this is a positive charge here, and you're trying to get it to a more positive location, it's hard to get it up there. It's hard to get it up there. It takes energy. It takes joules to get it up there. And the bigger the charge is, the more joules it takes. So the unit of potential, sit down in your seats here, I know it's exciting, is the joule per coulomb. That is the unit of potential. Think about that. It's the amount of energy it takes to get a certain amount of charge from one point to another. The bigger the potential, the more energy it's going to take to get a certain size charge there. The bigger the charge, the bigger the number of coulombs here, the more energy it's going to take to get up to a certain potential as well. So this is the unit of potential. The other thing to keep in mind is 1 joule is equal to 1 Newton meter. A joule is equal to a Newton meter. If you think back to Physics 1, first semester physics, we talked about that. Unit of energy, a Newton times a meter, force times distance. That's energy, a joule. So this over here, if you look at it, a Newton meter per coulomb is a joule per coulomb, which is equal to a volt. So, in essence here, this result that we calculated is a number of volts. It's 1.13 times 10 to the 6th volts. A volt is a Newton meter per coulomb. I'll write that obvious somewhere here. Write it right here. 1 volt equals a Newton meter per coulomb. I wrote it up there too, but I want to make sure that this is completely clear to you. That is the unit of a volt. So you get all these interesting combinations of units that we encounter in second semester physics, how different things are related in ways we may not have expected. And this is how a volt is related to Newtons, meters, and coulombs. Great. I also asked you to calculate what is the potential here. The potential at this point is 1.13 times 10 to the 6 volts. What's the potential halfway through between 0 volts and 1.13 times 10 to the 6 volts? Well, let's see. Calculating voltage, it's electric field times distance for when the electric field is uniform, which is what this is. So I'm going to do that here. The distance earlier was 10 to the minus 4 meters, which is 1/10 of a millimeter. The distance now is 0.5 times 10 to the minus 4 meters. If we do the math there, we'll see that directly in between these two plates here, the voltage will be half of what it was earlier. So it'd be about 0.56, maybe 0.57 times 10 to the 6 Newton meters per coulombs, which is volts, as we discussed. Okay? So that is, or if you like, 5.7 times 10 to the 5th volts is the potential here, and 11.3 times 10 to the 5th volts, or 1.13 times 10 to the 6th volts is the potential here. All right, so that was this problem that we started in the last video. We already mentioned that. So now, let's say that each plate is an area. So this is a plate, remember. This is a plate here. This one's a plate here. They're identical, except one of them is a positive charge and the other one is a negative charge. So what can we say about, let's see here, make sure you can see all this. dangerous. I can't see very well what you can and can't see, but I want to make sure you can see everything. So I'm going to erase a lot of this stuff, but I want to go to the next question, which is on this next slide in the PowerPoint, and that is, how much charge is on each plate if the area of each plate is 100 square centimeters, and if the field between each plate is what we've been calculating. We already calculated the charge density on each plate, or we were given that earlier. It was 0.1 coulombs per meter squared. So how many coulombs is going to be on the plate that has 100 square centimeters? So I'm going to erase all this stuff here. Okay, I apologize. I didn't want you to have to watch me doing all that erasing. What I have here is my 100 centimeter plate, square centimeter plate. So it's 10 centimeters on each side. So that gives it an area of 100 centimeters squared. And I was given in this problem, I told you that the charge density is 0.1 coulombs per meter squared. The question then is, how many coulombs does it take if the plate is this big to give me that charge density? That's what I'm asking. So how much charge do we need? To end up with this. Okay, so that's the question. And let's figure it out. So sigma is equal to the amount of charge divided by the area. And this is what I'm looking for, so I could say the amount of charge is equal to sigma times the area, where sigma is the charge density and A is the area. All right, so that's going to be equal to 0.1 coulombs per meter squared times the area of 0.01 square meters. That's equal to 0.001 coulombs. Okay, 0.001 coulombs is equal to 1 times 10 to the minus 3 coulombs. That's how much charge we need on each plate. The positive plate will have positive 1 times 10 to the minus 3 coulombs. The negative plate will have negative 1 times 10 to the minus 3 coulombs. That's what's meant by the charge that we're going to put on each plate to get that charge density. And of course, as we add more and more charge to each plate, we're going to strengthen the electric field. We're also going to increase the potential difference between the plates. So conceptually, that's what's going to happen. And that's actually what happens in a capacitor, which is when you have two plates that are identical, except that one of them has positive charge on it, the other one has negative charge on it. And we're looking for the electric field between the plates and the potential difference between the plates. And that's what this picture is here, and that's the symbol for capacitor. So when you see this symbol here, that means capacitor. And it's exactly as it looks. There's two plates separated by some space in between them. And I'm going to define capacitor, or capacitance. Okay, it's equal to the charge that you put on these plates. And so I would say here, what do I mean by charge? I mean the total amount of positive charge, which is going to be equal to the total amount of negative charge. So if I say a charge Q exists on this capacitor, there's charge Q on it. What do I mean by that? It means that this side here is plus Q, and this side here is minus Q. That's what's meant by having a charge on a capacitor. And the capacitance, I'm going to erase all this. I'm going to try to get this done and then finish this video off so it's not too long for you. Then I'll create the next video. Capacitance is equal to charge divided by the potential difference between the plates. Because clearly, this side is going to have a positive potential, this side is going to have a negative potential. We'll often take it to be 0. The potential difference that we measure across the plate is V. That's what you get by putting the negative terminal of your meter here and the positive terminal of your meter there. Remember, the meters are these things that you used in lab that I'll be using again in this week's lab. All right, so this is the equation for capacitance. You might also see it like this, and I like using the acronym that the charge is equal to the capacitance times voltage, or Chula Vista. Some of you might be from Southern California. That's a nice little mnemonic device I use to remember what is meant by this. Okay, I'm going to take this equation here, and I'm going to come up with an expression for capacitance that doesn't have any Q or any V in it by dividing these two quantities based on what we know and based on everything we've done so far. You're going to be amazed by this. And so again, you're going to be chomping at the bit for that next video. So hold on, I'll get it produced as quickly as I can. All right.